So this is topic 3, the discriminant and solving quadratic equations. So when you're solving a quadratic equation, sometimes what you want to do is convert it into vertex form, because vertex form is very helpful. You have the vertex, and then you can get the axis of symmetry from that, and it's just easier to work with, in my opinion. So if it's not already in vertex form, if it's in standard form, you want to do something called completing the square to get it into vertex form. And this is how I do it. So, for example, you have the standard form, which is an ax squared plus bx plus c, and then you want to convert it into this vertex form. So, the textbook example is y equals x squared minus 4x minus 1, and how they did it is they add this 2 squared in red, and the reason they do this is because when you want to get into vertex form, you notice that it's x minus h squared, and so that means that the thing has to be converted into a perfect square to get it that way. Like, for example, if you have this x squared minus 4x plus 4, that's a perfect square, and you can factor it into x minus 2. But it's not in that yet. So how do you get that to be a perfect square so that you can condense it into that perfect x minus h squared form? Well, how you do it is that you add a c value that would make it a perfect square. And see how there's 2 red numbers, the plus 2 squared and minus 2 squared? Well, technically they cancel each other out, so you're not actually adding or changing the equation. You're just adding this number and subtracting it, so technically it's 0. So they didn't do anything major to this equation. They just reformatted it. And so when you do that, you will get x minus 2 squared, because when you have the 2 squared, you get 4, and x squared minus 4x plus 4, that converts into this, but then you get all this extra junk, and then that is minus 3. So I'm going to take an example, and I'm going to convert it into vertex form and then graph it. I'll show you how to do this. So this example is page 50, number 3, and it is draw the graph of y equals negative x squared plus 2x. And so you want to convert it into a vertex form, right? So how are you going to do this? Well, first you have this negative value in front of the x, and you don't want it. So use the distributive property to take out the negative 1 from both the x terms, and then you'll get minus 1 parentheses x squared minus 2x, and then you don't want this negative. So when you don't want something and you're converting it into a vertex form, basically what you do is you just shift everything to the y. So what we're doing here is we're shifting it to the y, so it will become negative y equals x squared minus 2x. So now, what do we do? Well, remember from when I said the completing the square, you want to find a c value or a third polynomial value that will complete the square. But at the same time, you also want to subtract it so that the net value is 0. So how do you find this? Well, if you look at it, it's ax squared plus bx plus c, right? So look at the value. There's no c right now in the negative x squared plus 2x. So you want to add one. The b value is negative 2. So how you find the c from this b value is you divide it by 2 and then you square it. So let's take a look at the expression a plus b parentheses squared. You would expand that expression like parentheses a plus b, and then times parentheses a plus b, and then you would FOIL it to get a squared plus 2ab plus b squared. So if you're trying to find a term to complete the square, you need to find something that corresponds with this expanded expression, and that would be b squared. So how did you get b squared? Well, look at the term 2ab. You got b squared from that by dividing it by 2 and then squaring it. So that's what we're going to do to find c, or the b squared term in that case. So now we have this c, which is 1. So if you try that, you plug that into the equation. So negative on both, basically you add it on both sides, which ends up being 1 minus 1 if you place everything on the other side. So we're basically following the example that they gave us in the textbook. But this makes a little more sense if you add it on both sides, basically. So now you want to have y equals something something, because if you have everything at the y, it just looks really messy, and you want to convert it to vertex form, right? So you just take that 1 that's in front of the y, and then you put it on the other side. So you subtract 1 from both sides, and then you get negative y equals parentheses x minus 1 squared minus 1. And then you want to shift that negative 1 from the y side to the x side. So you multiply everything by negative 1. And this part is really important. You don't just multiply the negative 1 with the x minus 1 square term. You also want to multiply it with the 1. So this 1 changes from a negative 1 to a plus 1. So your finished product should be y equals negative parentheses x minus 1 squared plus 1. So now we're going to graph it. So now you have it in this vertex form, right? This negative x minus 1 squared plus 1. Well, now if you know vertex form, you'll know that the vector is h and k. And if you look at this format, or the vertex form, it's minus h and then k. So for that, you should always find the opposite of what h is. And in this case, it's negative 1. So what's the opposite of h? It's 1. So the vector here is 1, and then the k is also 1. So the vector is 1, 1. Now, we're going to find the y-intercept of the equation. And it works on basically the same idea for any function. If you plug in a value for x and then you solve the equation, you should get y. So you plug in 0 for x, so that would be negative 0 minus 1 squared plus 1. And then 0 minus 1 is 0 minus 1 is negative 1, and then you square that. You get 1, but there's a negative 1 in front of that, so it's negative 1 again. And then negative 1 plus 1 is the little plus 1 at the end here. That is 0. So your y-intercept turns out to be 0, 0. So now you probably need a third point to cover this. The vertex, probably a y-intercept, and a third point. So the next point would probably be 3, because, okay, so if you look at this graph, we plotted in dark red the 0, 0 and the 1, 1. This is the y-intercept, and this is the vertex. So as you can see, if you mirror everything, because the parabola is mirrored, then the next red dot here would be 3. So you plug in 3 here. So 3 minus 1, and then that becomes 2, and then you multiply everything. That's negative 4 plus 1, and then negative 4 plus 1 is negative 3. So the x value is 3, so the answer is 3 and then negative 3. So that's another set of coordinates that you can use in your graph. So let's take a look at this again. So you plot all the points, remember, the y-intercept, which is 0, 0, the vertex, which was 1, 1, and then the other 2 points. I remember the axis of symmetry is going to be the x-coordinate for your vertex, and remember the x-coordinate for our vertex, which is 1, 1, should be 1. So our axis of symmetry is just going to be x equals 1. And then so you just flip everything, every coordinate that you got. And then when you're done, just trace the points and you'll get a parabola. So that is how you do completing the square to graph a quadratic function. So now the next topic we're going to be moving on to is the discriminant. And do you remember the discriminant? Oh, oops. This should be squared, I'm sorry. But the discriminant function, or expression, is b squared minus 4ac. And if you remember the quadratic formula, which is opposite b plus or minus the square root of b squared minus 4ac divided by 4a. So that's just taken from the quadratic formula. And this triangle here, or delta, it represents the discriminant, and it's just a review. So if the discriminant is less than 0, there's no real roots. If it's equal to 0, there's 1 real root. And if it's greater than 0, then it's 2 real roots. And basically, how many roots it has is basically how many times the equation goes through the x-axis. So let's look at an example to show you what I mean. So here is an example that the textbook gave us. Y equals x squared plus 3x plus 4. And if you look at the a, b, and c values, because it's in standard form, so that is really helpful. The a is 1 because you have one of the x squared terms. The coefficient of b is 3, and c is just 4. So you plug that into the discriminant, which is b squared minus 4ac, and you'll get 3 squared, b is 3, so 3 squared is 9, and then minus 4, which is just part of the discriminant. A is 1, and c is 4, so 4 times 1 times 4 is 16, and then 9 minus 16 is negative 7. That means that the discriminant, which is negative 7, is less than 0, which means that there is no real roots. Also, if you take a look at a, the a is greater than 0 because it's 1, so that means the graph goes up. If it's negative, the graph will go down. So here's another example from the textbook, and that is page 51, number 5, and that is find the nature of the solution of 2x squared minus 5x minus 7 equals 0. So let's pull the a, b, and c values from the standard form. So you know that a is 2 because it's 2x squared, and then b is negative 5, and c is negative 7. So again, you plug it into b squared minus 4ac, and you get negative 5 squared minus 4 times 2 times negative 7, and then you get 25 minus 8 times negative 7, which is 25 plus 56, and then you get 81. And 81 is obviously greater than 0, which means that the discriminant is also greater than 0, which means that there are 2 real roots in this equation. So what does that mean by 2 real roots? Well, it goes through the x-axis 2 times. So if I graph it, here's the graph of that expression. And you'll see that it goes through this x-axis 2 times, which means that it's 2 real roots. So that is how you find the discriminant and how you use it to determine how many roots it is.